So today we'll be solving a longitude by chronometer question for moon as a celestial body. Alright, so longitude by chronometer method is also called long by chron. That's the short form by it. And my previous videos have discussed the same method using the sun and the star and the planets as an example. So this video focuses purely on moons as a celestial body. Alright, so I'll go with the question. The question says that it's 25th of February 1992 and it's morning on your ship, so it's AM on your ship, and your dead reckoning position or your DR position, the estimated position, is 20 degrees 04 minutes south and 0904 minutes west. The sextant altitude of the moon's upper limb or UL was 52 degrees 26.8 minutes at chronometer time 2 hours 56 minutes 17 seconds, with the chronometer error 4 minutes and 01 seconds fast. Height of eye was 19 meters. Index error was 0.6 minutes off the arc. You have to find two things. You have to find the direction of the position line and a position through which it passes. Alright, so when we say you have to find the position through which passes, you basically are finding the observed longitude only, and you use the same dr latitude as your final latitude through which the position line passes. And then of course you have to find the direction of the position line. Alright, so let's start with the question. But before we do, we have to solve the ambiguity of chronometer time. So if you have not watched my previous videos, I've discussed this many times, and there's a separate video titled ambiguity of chronometer time. Please watch it so you will know what is ambiguity of chronometer time and why it occurs. But I'll quickly show you the method of finding out the or solving the ambiguity of chronometer time to find the GMT, the date and time of GMT. Alright, so if we are given a chronometer time, just add 12 hours to it. That means that when it's 2:56:17, it could be 2:56:17 in the morning or 2:56:17 in the afternoon. So you have to have two scenarios and then work out which is the correct scenario on your ship. Alright, then the error is fast. Whenever the error is fast, you will subtract the error. If it is slow, you will add the error. So do the same thing for both the cases. You get the GMT time. Now you get two possibility scenarios of GMT, and you have to find out which is the correct one. To do that, you apply a correction called the zone correction. As you can see here, it's a zone correction. Zone correction you get from calculating the longitude in time, or the LIT. So LIT stands for longitude in time, which means that every ship has its individual time based on the longitude through which it passes, or through which the longitude through which the passes through the ship, rather. But this is not a practical way of timekeeping. The practical way of timekeeping is the zone, because you cannot have individual times on your ship based on your longitude. You need to have a time all the ships need to have a time based on the zone in which you are, that is between the range of longitude. So if you are in port, you cannot have an individual time. You need to have the same time as that of the port for practical business to take place. Alright, so but to get the zone, you actually have to calculate the longitude in time, or the LIT, by dividing the dr longitude in this case by 15, because the world is divided into zones and each zone is at a range of about 15 degrees of longitude. Alright, I've talked about all this before, so I'm just repeating myself for those of you who maybe this is the first time you're watching my video. I'm just repeating myself. Please watch my other videos, and I've repeated the same information every time. Alright, so anyhow, you calculate longitude in time dividing the dr long by 15, which is 90 degrees 4 minutes divided by 15. You get 6 hours 0 minutes and 18 seconds. You write your LIT in minutes, hours, minutes and seconds, but the zone is always a round number. It's a whole number, because that's the correction you apply to the GMT. So because your LIT is closer to 6 hours or 6 o'clock, that's the zone I will take. If it was close to 7 o'clock, I would have taken 7, but in this case it's very close to 6, so my zone will be 6, because I need a whole number. So that's the zone I take. But we are in west longitude, so my zone will be minus. That's because when you're in west longitude, GMT is ahead of you. That means the time at GMT is more than the time on your ship when you're in west longitude. It's the opposite when you're in east longitude. When you are in east longitude, you are ahead of GMT. Time on your ship will be more than the time at GMT. So that's why you subtract it. So the second case, of course, you subtract 14 minus 6, you get 8 hours 52 minutes 6 seconds. In the first case, if you're wondering how I subtracted the bigger number from the smaller, we'll just add 24 hours to it. Make this the bigger, then you can subtract it off. All right. Now this zone time is also called ship's mean time, or SMT. This is the time on your ship. Now if the time on your ship, there is two scenarios. How do I know which is the correct scenario? Well, I'll use the hint given to me in the question. The hint given to me in the question is that it's AM at my ship. That means it's morning on my ship. And if it's morning and it's 25th of February, only the second case makes sense. So this is 25th of February, it's morning 8 o'clock here. It cannot be 100 hours. And if I subtract 6 hours from, so even though GMT is ahead of me, it's still 25th of February at GMT. So I don't need the first case. I'll cancel out the first case. So that's why my GMT becomes 25th of February, 14 hours 52 minutes and 16 seconds. All right. Don't make a mistake and start working with the zone time. Some students do that. Make sure you only work with the GMT time, because that's the time that is used in the nautical almanac to provide us with the GHA and the other corrections. So I'll have to find the GHA for 25th of February from the nautical almanac of 1992. So I will find it first for 14 hours when I go into 25th of February. Then I'll find out the increment, which is always added, for 52 minutes and 16 seconds. And then I will find out the V correction. I'll show you where all these values is from. So the V value of 9.7, where did I get it from? I'll show that all that to you. Alright, so let's get into the nautical almanac for 25th of February 1992. Alright, so 25th of February 1992, 1400 hours. So this is my nautical almanac for 1992. This is 25th of February 1992. Moon is here, right? And I need it for 25th is here. So I'm not zooming onto the moon, because otherwise then you don't get an idea of what I've done. So if I zoom onto the moon, you can see that these are the values given. You can see it more clearly, right? But then I lose the GMT time given to me on the side of the paper. So that's why, unfortunately, I can't zoom in. This is the best I can do probably. Alright, so then you can see the 14, I need to make it normal. That's right, this is better. So I need to switch on my pen again. So this is my 14 hours on the, alright, so if you follow this horizontally, you will get to the moon's GHA. This is the moon's GHA. This is the GHA of moon. The next column is the V value of moon, so GHA. So 9.7, we'll be using this value as well. And then you've got the declination of moon as 24 degrees 16.3 minutes south. So this is 24 degrees 16.3 minutes south. The declination is increasing to the next hour. So, and then the D value is here. So the declination is here, D value is here, and the D value is 2.3. So we'll be using all these values. Alright, so I'll erase this just for you guys to see it again. So you can see that the moon is here, the GH is here, V value is here, declination is here, the D correction value, or the D value for the declination correction is here. We'll be using the D value and the V value and going into the increments pages at the back of the almanac to find the correction value. For now I am showing you just the GHA and the V, the declination and the D. We'll be also using the horizontal parallax today, so I'll show that to you as well when I come back to it later. Alright, so let's go back into the solutions. I can show that to you. So I hope you noted down those values, and you can see that's how I found my GHA. Alright, and I found my V, I found my declination. Since it was increasing to the next hour, my D value is here. I will be adding it, and then if I add, then I'll show you now where I got my V correction and my D correction from for 52 minutes and 16 seconds, and I'll also show you my increment. Alright, let's go back. So here it is. So increments for 52 minutes and 16 seconds will be here somewhere. Right, so this is 49, 52, 52 is here. Right, so I'll activate my pen. This is 52 minutes and 16 seconds is, so my moon is here, right? 16 seconds is here. My moon increment will be here. Alright, so is that the 52 minutes 16 seconds? Yes, 1228.3, and then my V is 9.7 and D is 2.3. So V and D correction is you get from these columns here. So V of 9.7 is here. So the V correction is 8.5 and the D is 2.3. So the D correction is 2. Alright, so you can pause this video at this stage here and just have a look again how I got these values. I'll keep going because you can pause it. I can't, I have to keep going, but have a look at these values again. These are the increments and the corrections pages. Normally they are at the back of the almanac, and just go into the relevant minutes and minutes section and you will find out the increment and the V correction for the V value and the D correction for the D value. Alright, and then I'll go back into the solution so that I can continue with the question. Alright, so this is where I got my D correction from, my V correction from, and my increments from. So you will add the increments and the V correction, you get the GHA. This GHA is for 14 hours and 52 minutes and 16 seconds for the 25th of February. And you also get your declination. And the DR lat is given to you in the question. Then we start working or calculating the sextant altitude. Rather, the sextant altitude given to us, so we start deriving the true altitude from it. Sextant altitude given to us is 5226.8. The index error is given to is off the arc 0.6. When it's off the arc, you will add it. Whenever it's off the arc, you add it. If it's on the arc, you subtract it. Once you add the index error, you get the observed altitude. So this is the observed altitude. And then you have to find out the dip or the height of eye correction. So the height of eye correction for 19 meters. Alright, so I will go into the relevant pages of the nautical almanac, and this is where I have to show you. So where I got my horizontal parallax from, remember I showed that to you as well. So well, let's go into the pages. So dip of 19 meters. So normally we have a height of eye page table for sun, stars and planets and all that. Today I'll show you another table or another document that we have, and I'll show that to you as well. So these are altitude correction tables given to you at the back of the almanac as well. These are probably the last few pages after the increments pages, and these are the pages given to you. Alright, so this is where you can find out your moon's height of eye as well. So you can see the dip column here. Why is my black pen activated? But this is the dip column. Alright, so for a height of eye of 19 meters, which will be lying somewhere here between 18.8 and 19.3, you get minus 7.7. This is where you get it from. Alright, so I'll go back and you can see it's minus 7.7 here. So height of eye is always negative, so you will always subtract it. You get your apparent altitude. And then you have to find out your main correction, your horizontal parallax correction. And you have to find out where do I get from. So to do that, I'll show that to you. But I have to show you where I got my horizontal parallax value of 55.4. Alright, I was showing it to you earlier, but probably you didn't notice it. So I'll go back to 25th of February in the nautical almanac, and then I'll show you there. Alright, so I have to get out of this document, go into the 1992 almanac. So for 25th of February, which will be somewhere here, you can see that the horizontal parallax value of 55.4 is here, right? So you can see 55.4 is the one that I will be taking for 12 hours, 13, 14, all these hours. 55.4, then it changes from 55.3 from 1500 hours. So for us, it will be still 55.4. This is the horizontal parallax value, HP. Alright, it's not, doesn't stand for Hewlett Packard, it stands for horizontal parallax. Alright, so with that, that's the value. So now you must be wondering where I got my main correction from. So my main correction and horizontal parallax correction is from the same pages, and that's why I thought I'll show you how I got my horizontal parallax value from. Alright, so I'll take these values and go into the pages. So remember, you have to remember your apparent altitude value or your apparent altitude value here, which is 52 degrees 19.7. Alright, so I'll go back here, and what I need to do is I go back to the corrections for the moon. So we have to go back to this page here, which I was showing you earlier. These are the last couple of pages in the almanac. So I'll go to the next page. There are two pages here, and you can see that 52 degrees 19.2. So your apparent altitude values are given here. Keep sinking to the black, and 52 degrees will be somewhere in this column here. So you can see 52 degrees here. 19.2 minutes will be very close to 20 minutes. So my main correction, which is 45.2 here. Alright, and then my horizontal parallax values are given here. 55.4 is between 55.2 and 55.5, and these are your upper limbs. So it will be very close to 2.9 because it's 55.5. So that's why, you know, this is my upper limb value, this is my horizontal parallax values. So if you go straight here, you will see it's about 2.9. Alright, so you get it. So the horizontal column here is apparent altitude, that's in degrees. All this is in minutes, and that's why I went to 52 degrees, which was your apparent altitude value. 19.2 will be very close to 20, so that's why you get your main correction is 45.2. And with your horizontal parallax, you get your another correction here for your upper limb correction. This is your U stands for upper limb, L stands for lower limb. Horizontal parallax was 55.4, so I came very close to 55.5, and then I went horizontally. For upper limb it's 2.9. So this is where you get the values from. Alright, so hope that was easy enough for you to understand. And then the sign, of course, it's all positive. The sign will tell you what to do. So you add it to the apparent altitude value and you get your corrected apparent altitude of 53 degrees 7.8 minutes. Now what happens is, with upper limb correction, no matter what, after all these corrections you have to apply a negative correction of 30 minutes. This is also written in these pages here. If I can show you, I'll show it to you. It's written here even in the moon correction tables, as you can see. And if I can highlight it to you, you can see this portion here. It tells you to do that. So you can see 30 minutes is to be subtracted from the altitude of the upper limb. Now this is only for the upper limb, alright, not for the lower limb. So whenever you see upper limb, you have to apply a negative correction of 30 minutes. And once you do that, you get your true altitude. Alright, once you get your true altitude, subtract it from 90 degrees and you get your true zenith distance, which also is written as TZX, or sometimes in some books as TZD. So this stands for true zenith and distance. Alright, once you get your true zenith distance, so you have subtracted 90 degrees minus true altitude, then you just use a scientific calculator and put the values here. So cos of LHA equals sine of true altitude, plus or minus sine of lat, sine of tech, divided by cos of lat and cos of tech. Now plus or minus depends on if latitude and declination are same names, you will minus it. If that is, if both are north or both are south, you will use a negative here. But if latitude and declination has different names, you will use a positive sign. So this depends on the names of the latitude and declination. In this case, they are same names. Your latitude is also south and your declination is also south, as you can see here. So you will use a negative sign. So your cos of LHA, which is also denoted by P in this case, you can call it P. I'll tell you why all this happens and later on as well, is just put in the values here. So you know your true altitude value, your latitude and declination value, just put the values here and then see how I have calculated the values. You should be getting the same values. So I put these values so that you can match it with your one in the calculator. So I stick to about 5 decimal places. You can go more if you want to, but don't go less, because the more the number of decimal places, the more is the accuracy. So once you solve the right hand side of the equation, take cos to the other side, becomes cos inverse, and then you get your P value of 40 degrees 14.1. Now the long by chron method that we are solving today is used to calculate the observed longitude. So although the longitude is given to you in the question, that is the dr longitude, that means that's the estimated longitude. You are not sure whether that's the correct longitude or not. So you have to find the observed longitude. To do that, there is a rule that once you find out P value, which is also the LHA, but we call it P because the rule for long by chron is that if it's before meridian passage of the celestial body. What is meridian passage? Means the celestial body is exactly on the observer's meridian. If the observer's project, that is you, observer is you on the ship. So if I project your position onto the celestial sphere, and if this is the celestial sphere, and if I project your position here, and this is you, Z here, then when the body is here exactly over you, denoted by X, on your meridian, alright, it could be on your meridian, it could be here or here, it doesn't matter. That is meridian passage. So if the time at which the site was taken is before meridian passage, then LHA is equal to 360 minus angle P that you have calculated. If it is after meridian passage, then P only becomes your LHA, and that's why the confusion above that I have put LHA and P together. Alright, now how do I know this is after or before meridian passage? Because it's early in the morning, it's 9 o'clock in the morning, so it cannot be moon's meridian passage. That is the time. So meridian passage happens when the body rises, reaches its peak, and then sets on the west, right? So at 9 o'clock in the morning, the moon cannot be rising still. The moon must be setting, so it must be after meridian passage, right? So why I said it's morning? Because the question says it's morning on your ship, right? That's why it's after meridian passage. That means your P that you have calculated will also be equal to your LHA. So in this case, angle P equals LHA, which is also equal to 40 degrees, 14.1 as calculated by you above. Okay. Then your GHA that you have calculated is 130 degrees, 20.3. You know you're in west longitude, longitude west. GHA is best. That means GHA should be more than LHA. GHA should be more than LHA. Alright, GHA here is more than LHA, so you will subtract the LHA from GHA and you get your observed longitude. You are in west longitude, so it's 90 degrees, 6.2. Conceptually, if I have to understand this, then GH is nothing but angle between the celestial Greenwich meridian, denoted by GM, and the celestial body. So this is GHA, measured westwards from the Greenwich meridian. What is LHA? LHA is measured westward from the observer, which is you here. And I apologize for my poor drawing. This is the moon here. This is you here as the observer. Alright, measured westward from the observer. This is your LHA. And finally, what is the longitude? I should change my pen. Is from the Greenwich meridian. It can be measured east or west, depends on where you are, and this is your longitude. And then you can see that you are on the west side of the Greenwich meridian. That's why your longitude in west. So if you put in the values here of in the diagram, you will find out that your longitude is correct. Alright, so although LHA is measured westwards, and GH is also measured westwards, longitude is measured east or west depending on where you are as an observer, on the east of the Greenwich or west of the Greenwich. That's how I calculate my longitude. So the final position will be, of course, the position through which the PL passes, position through which the position line passes. That is the question asked to you in the question. That's the question asked you, right? Position line passes. It should be line, not lines. Alright, so position line passes. So you will use your dr latitude and you will use your new observed longitude. That's the answer. Alright, dr latitude is given to you in the question and the observed longitude is the one that you just calculated. So now we move on to the second part of the question, which says calculate the position line. To calculate the position line, you have to calculate components of A and B. Component of A is calculated by dividing tan lat by tan LHA. Put in the values here. If there is a negative sign, ignore the negative sign in the calculator. Just put in the value. You will get 0.43. I stick to normally 2 decimal places. You can go more if you want to. And then you will name it. How do I name it north? Well, it's named opposite to your latitude, unless LHA is between 90 and 270. Your LHA is not between 90 and 270, so you will name it opposite to latitude. So latitude was south, you will name it north. B is calculated by dividing tan dec by sine of LHA. Put in the values here. If there is any negative sign, ignore the negative sign in the calculator. Just simply put in the value. You can go more decimal places if you want, and then you name it. In this case, I have named it south. Why? Because it's named same as declination. Whatever is your declination, you will name it same. So if your declination is south, you will name B south. Then just put in the values here, A and B. The rule is if they are different names, you will subtract it. So since they are north and south, you will subtract it. If they were same names, you would have added it. So if they were both north or both south, you would have added it. So you subtract the smaller number from the bigger number and then retain the name of the larger. So the larger is here, retain name of larger. Alright, so your larger is B south, so that's why you will name C south. C is not negative, it's always positive. Okay, so just subtract the smaller number from the bigger number. It doesn't matter if A is written on top and B is written below. And the final thing is you have to calculate the tan of azimuth. Azimuth is the bearing that will give you the position line. The formula is 1 divided by C times cos of lat. C, you know from above, is 0.27. Latitude is given to you as the dr lat, right? Solve the denominator first and then divide 1 by it. Take the tan onto the other side here, becomes tan of inverse, and you will be getting somewhere around 75.8. I like to round off the bearings. You can continue with decimal. Both the cases they are right. Depends on what your lecturer is teaching you and what he wants in the exam or in the answers. Some books you continue with the decimal. I like to round off the bearings because I get into the habit of plotting these bearings on the chart. So otherwise you continue with decimal, doesn't matter. So just round it off to the closest number, which is 76 in this case. And then you can see I've written a south and a west here. Now where do I get this from? Well, south comes from name of C here. So south is name of C. Whatever is C, I name it that. And west comes from the LHA. So why? Because if LHA is between 0 to 180 degrees, I will call it west. If LHA is greater than 180 to 360 degrees, I will call it east. Your LHA was about 40 degrees 16.2 or something, isn't it? 40 degrees 14.1. So that's why I will call it west. So south 76 west is also equal to 256 degrees, which is a true bearing. Why is that? Because if this is south, which is 180, and this is west, which is 270, south 76 west means you went from south, you went towards west by an amount of 76 degrees. That's why this becomes 256 degrees, right? As you're going from 180 to 270. Once you get your bearing of 256 degrees, to just subtract 90 and add 90 to this bearing. If you subtract 90, you get 166. If you add 90, you get 346. That becomes your position line. So PL stands for position line. So this is the position line that will pass through your observed positions with a DR lat and observed long. Alright, so this basically means you draw the DR lat and long. So this becomes the DR lat. This becomes the observed long that you have calculated. And your position line of 166 to 346 will be in this orientation here. That's what it means. So this is 166, this is 346. Alright, so I hope this video was easy for you to understand. If you have any questions, please write to me in the comments. And thank you to all my lovely subscribers and people who watch these videos and provide me with feedback. Really appreciate it a lot, good and bad both. Thanks guys, and I'll see you soon with my next